All right, what? Welcome to Logs Vlog or Vlogs with Log or what? Okay, let's calculate energy today. First off, we've already talked about how reactions that give off energy are exothermic and the change in energy would be negative. We talked about how energy can be written as a reactant or a product depending on if it's endo or exo. We're going to get to the point where we're going to write a balanced equation and throw energy into it. So right now, today, let's talk about how we calculate energy. First off, there are two units that we use to represent energy. One of them, like I've already said, would be a part of my rap name if I had one, and it would be joules. This is kind of our metric unit used worldwide. Sometimes you'll see just a capital J written. We've seen that. We've also seen KJ for like kilojoules written as well. Here in the United States, though, that's not a really common unit for us here. We like to fly solo, have our own kind of unique units. Here in the United States, to represent energy, we use calories. Now, don't be confused here. In the United States, we've got two types of calories, one with a lowercase c and one with a capital C. This guy is what we see on dietary food labels. But really, what it is it's the same thing as a kilocalorie with a lowercase c. So here's kind of how we do these conversions here. A calorie with the lowercase c, 1, is equal to the amount of energy you have to add to 1 gram of water to heat it up 1 degree Celsius. We call that a lowercase calorie, okay, 1 calorie. That is equal to 4.18 joules of energy. So in order to heat up 1 gram of water 1 degree Celsius, you have to add 4.18 joules of energy to it. Which means on our food label, so if you've got something that has 1 calorie, which is the same thing as a kilocalorie, that's the amount of energy it would take to heat up 1,000 grams of water 1 degree Celsius. So think of how crazy that is. That's so much energy in a dietary calorie. It's pretty awesome. We take a lot of energy to function. Do want to tell you, we're going to see temp involved in this since we are talking about a transfer of heat. But usually we're not going to be talking about gases. So, like last unit, or unlike last unit, I'm going to ask you to ditch Kelvin. You don't need to worry about it. That's only when we're talking about ratios and changing sets of data with gases. This unit, we can keep everything in Celsius, so don't let that scare you or stress you out. Kind of moving forward. I know some of us forgot that on the test and the quiz from last unit. But I did just want to point out, if you travel to other countries at all and you look kind of at their food labels, they will list the amount of energy in kilojoules on their label. So in other countries, instead of counting calories, they're counting their kilojoules. I'm not me though. In class, I just think it's fun. I like Chipotle. I would have us do some conversions with that. I'm not going to spend any time doing this. This is not something that would be on the test, but my burrito takes 975 calories, and I've eaten 2 in one sitting before. Beast. And you know what? I will not ever run a marathon, so I'm going to skip that question too, so don't worry about it. If you took AP Bio or remember food, sorry, if you remember talking about food chem, biochem in biology last year, our body's main storage molecule that we use are fat molecules, and they're awesome at storing a lot of energy fairly compactly. And so for every 1 gram of fat that gets absorbed or eaten, you take in about 9 calories of food. So it's the most kind of calorie dense molecule that we can take in. And then, boring. But here, Michael Phelps, when training for the Olympics, he'd have to take in a 12,000 calorie a day diet just to keep up with all of the workouts and stuff that he was doing, which I think is crazy. So if you're bored, flip through it. Maybe this could be like a YouTube challenge video that we try and do in here. I feel like I could eat breakfast there. I could do that. I don't know about the pound of pasta and the energy drinks is kind of what I probably couldn't do that. No, We can dream. To calculate heat, they use the letter Q to represent heat or the energy involved. Makes sense. But they take the mass of, I'm going to write the substance being heated. This is going to be your new favorite equation. And they multiply it by what is called the heat capacity. It's a constant, and it's a constant depending on which substance we're talking about. I'm going to write or specific heat. So it's kind of the two terms you'll hear it refers to, heat capacity or specific heat, and then times the change in temperature. Q equals MC delta T, you guys. Here's our equation that we use to calculate heat. Before I kind of jump in and have us manipulating this equation a little bit, I wanted to talk about this constant, the heat capacity. It's the amount of energy it takes to heat something up, 1 gram of it, 1 degree Celsius. So the one that we'll use quite a lot of, because it's one of the most common substances that we have here on this planet, is water. Water's heat capacity is 4.18 joules for every gram to heat at 1 degree Celsius. Or if you used it in calories, it would be 1. Water actually has a pretty high heat capacity. It takes a lot of energy to change water's temperature, which is why if you go to make mac and cheese now for lunch or for dinner and you go to boil water, the pot that the water is sitting in gets hotter faster than the actual water in the pot. Metal has a lower heat capacity. It's able to transfer and heat up faster than liquid water does. So that's kind of interesting. Aluminum's heat capacity is 0.897. Iron's heat capacity is 0.449. If you want to look up other heat capacities, Google it. Otherwise, if you grabbed a textbook before this whole thing started, I think in the back in the tables section, there's a table of heat capacities, but we're in chapter 16 if you ever get scared. So let's say we had 1 gram of water, 1 gram of aluminum, and 1 gram of iron. And let's say I added 10 joules of energy to each one of those. Which one of those will have the largest change in temp? So you have to think to yourself, which one takes the least amount of energy to change its temp? Well, that's iron on this list. So if I added 10 joules of energy to iron, it's going to have a greater change in temp than water will, because it takes way less energy to change its temp than water. The one that would have the smallest change in temp, I'm writing iron here so we don't forget, would be the one that takes the most energy to change its temperature. So water would have the smallest change in energy. So there's some questions we can ask from that, and then put some on the homework just to kind of practice that idea of that heat capacity for it, and how that applies to like its change in temp and how much energy it's absorbing. But what's kind of nice is it's pretty straightforward. So here's a problem. This question is asking us to solve for the heat. So that's asking us to solve for Q. So there's our equation. Q equals MC delta T. And in this case, it's ethanol. Oh, that clock. Burn it. Stop. It's not even the right time. Okay. Anyway, we have 35 grams of ethanol. And ethanol's heat capacity, so I'm giving that to you here, is 2.44, and I'm going to write the units, joules per gram Celsius. The energy it takes to heat up 1 gram, 1 degree Celsius, and we are changing its temperature 13.5 degrees Celsius. So here is some math magic. I'm going to switch colors just to make this like exciting. Celsius goes away, grams go away. Do you see how the one unit we're left with is joules? That's heat, that's energy. If I kept with the 3 sig fig idea, I think we get 1,150 joules of energy. Not bad, right? I can do it. You can do it. Here we are. Next one, we've got 15 grams, sample of gold and it absorbs this much heat. So that's Q. And the temp changed by 38.5. This is asking us to solve for C, the specific heat. So here's our equation again. If I solve to get C by itself, I'm going to do Q divided by the mass times the change in temp. So the energy should be in joules because C, the constant, usually is joules per gram Celsius. So I'm going to keep it as 74.5 joules, and I'm going to divide it by the 15 grams times the 38.5 degrees Celsius. And so I get as my answer 0.129 joules per gram Celsius with 3 sig figs. And this makes sense. Gold is a metal, so it's going to have a lower heat capacity than water. And gold is actually a really good conductor of heat, so it'll have a pretty low one. So, feeling okay? Okay, what's the only way to get good at this? Practice. Okay, try the homework that's posted.